in the previous lecture we discussed about the Stokes first problem. Today we will discuss about the Stokes second problem. Philosophically, what is the big difference? We will understand the difference once we state what is the Stokes second problem. So, Stokes second problem. So, Stokes problem is all about, you know, there is a plate and there is a sudden movement actuated on the plate and how the fluid on one side of the plate responds to that. So, in this case also there is an unbounded fluid in one side, but a major difference now is that this plate, instead of being dragged in one side, it is being oscillated, let us say it could be sine or cosine. As an example, I am taking sine. So, u equal to u0 sine omega t, where omega is the angular frequency at which this is oscillated, the plate is oscillated. So, now can you tell what is the big difference between this problem and the Stokes first problem? So, from the statement of the problem it is very clear that the oscillation frequency of this plate imposes a time scale to the problem. So, this is no more a problem without imposed time scale, this is a problem with imposed time scale. So, first from a mathematical perspective this problem will not be amenable to similarity solution and we have to adopt some other technique, but physically the more important consideration is that now there is an imposed time scale which is 1 by frequency of the this 1 by angular frequency of oscillation of the plate. Now let us say that we write the governing differential equation for this particular problem. So, if we write the governing differential equation, this is same as the, see the differential equation wise this is same as the Stokes first problem, only the boundary condition is different and that will drive to an entirely different type of solution. So, now let us do a little bit of scaling analysis of this equation before jumping on to the solution technique. So, the scale of u is u0, right, this is the scale of u. So, before doing the scaling analysis let us formally state the problem maybe on one side of the board. So, at t is equal to 0, u is equal to 0 for all y, at t greater than 0 u equal to u0 sine omega t at y equal to 0 and u is equal to 0 at y tends to infinity. So, this is the initial condition, these are the boundary conditions. This is a first order derivative in partial derivative in time. So, it requires one initial condition and second order partial derivative in space. So, it requires two boundary conditions. So, the scale u scales with u0, t scales with, now we know that what is the time scale imposed on the problem, and that will govern the physics of the problem. So, T is scales with 1 by omega. So, this let us write US Ts. So, now that means from a scaling analysis of this equation you will understand what is Y scale. So, to do that, you have the scaling of this is US by Ts, and the scaling of this is nu US by Ys square. Ys is the so called delta in the previous problem, or let us write delta to make a parity of the notations we have been using so far. So, now we can write that US by Ts is of the order of nu US by delta square. That means delta will be scaling with square root of nu by nu Ts. What is the Ts? Ts is 1 by omega. So, delta will scale with square root of nu by omega. This actually governs what is the physics of this situation. This delta scales with square root of nu by omega. So, the physics of the situation is like this: kinematic viscosity tries to diffuse the effect of the wall, but if you oscillate the wall at a very high frequency, then if you have a very high frequency, that itself will try to arrest the propagation of the disturbance, because once you have a disturbance, then suddenly, so once you have a plate movement, suddenly you change the plate movement, again you change the plate movement. So, you are repeatedly changing the plate movement, that means the fluid is not getting enough opportunity to digest the change. It is like somebody fed with one food after another food after another food after another food. The person has to digest the food and assimilate that, then only the effect of the food will come. So, this poor fluid, if it is forced with a high frequency, it will not have sufficient opportunity to digest that change. So, that means actually for high omega the delta will be less. So, we can say that the square root of nu by omega as a length scale, as a natural length scale, it governs the physics of the problem. So, now let us normalize the equation, right. Let us write u bar is equal to u by u0 or u by us. Then T bar is equal to T by Ts, this is omega T, and Y bar is equal to Y by delta. If that be the case, then this equation, because we have chosen the scales according to this equation, then this equation will boil down to this. Nu is absorbed in y bar itself. So, in this case, although you cannot use a similarity solution, you can still have a separation of variables, where one of the variables will be the spatial variable and in another, and the other variable will be the temporal or the time dependent variable. So, to do that, to come up with a solution of separable nature, you write u equal to so this is a particular technique where we assume the solution of this form. Now, there is a logic behind this, it is not that arbitrary we take this. Im is imaginary. See, this is a time dependent component, this is a position dependent component. Why the time dependent component is e to the power it? Because e to the power it is a combination of cosine and sine. Why the imaginary component? Because the boundary condition itself is sin omega t, which is the imaginary component of e to the power I omega t, and this t bar is omega t. So, that is why imaginary. Had the boundary condition been E0 cos omega t, then this would have been real. So, e to the power I t into a function of y. So, this gives a harmonic separable solution of time with another function with respect to y. So, physically what kind of function do you expect? So, this you expect a harmonic function of time, and this you expect an exponentially decaying function in space, because eventually as you go away from the solid boundary, there will be a critical distance delta beyond which its effect will be not there. So, this should be an exponentially decaying function physically. So, mathematically what it comes out, let us see. So, now as a shorthand we will equate this with this and basically not write the imaginary part time and again. So, if you write the partial derivative del u del t, then this is I e to the power I t f y del 2 u del y 2 So, we can say this. So, now let f equal to e to the power m y be a trial solution. This is a second order homogeneous ordinary differential linear differential equation. So, d2f dy2 is m square e to the power my minus I e to the power my is equal to 0 from here. So, m is equal to plus minus square root of I. So, the solution is f is equal to C1 e to the power square root of I y bar plus C2 e to the power minus square root of I y bar. This is the solution. Now, how will you get C1 and C2? For that you require to use these two boundary conditions. So, remember f is u by u0. So, you have u by u0, this is the first boundary condition, is equal to sin t at y equal to 0. T bar is omega t. So, now f was taken as imaginary, sorry, this is u bar not f. So, u bar is imaginary e to the power I t into f, right. This was u bar. So, now at y equal to 0, you have u bar is equal to sin t. So, imaginary of e to the power I t is what? It is itself sin t. That means at y bar is equal to 0, f must be equal to 1. Otherwise, these two will not match. This will not become sin t, this will become sin t when this is 1. When this is 1, imaginary e to the power I t is sin t, which is this boundary condition. So, at y equal to 0, f must be 1, and boundary condition 2 is that essentially u equal to 0 at y tends to infinity. So, in other words, u must be bounded, this is equivalent in this case, as y tends to infinity. So, it cannot be infinitely large. Now, if you see this form, if you allow this term to be there, then it can exponentially magnify u as y tends to infinity, but u has to be bounded. So, that physically tells you that C1 must be 0, and then at y is equal to 0, f is equal to 1, that means C2 is equal to 1, because if you put y equal to 0, f equal to 1, you will get C2 equal to 1. So, you will get the solution as f is equal to e to the power minus square root of I y bar. So, actually in a very neat and simple way we have arrived at the solution. So, you have u equal to imaginary of e to the power I t into f y e to the power minus square root of I y. Now, you can write square root of I in terms of I. How do you write that? How do you write square root of I in terms of I? So, I is e to the power I pi by 2. Why? Because it is cos pi by 2 which is 0 plus I sin pi by 2 which is 1. So, square root of I is this to the power half, that is e to the power I pi by 4. This is cos pi by 4 plus I sin pi by 4. So, this is 1 plus I by root 2. So, that means you have the solution u equal to imaginary of this non dimensional u, of course, e to the power I t into e to the power minus 1 minus I by root 2 . So, the solution is, if you take the imaginary part of it, okay. So, you can see there is an exponentially decaying part which actually spoils the harmonic nature of the solution. So, it appears to be a wave propagation problem, but it is not actually a wave propagation problem, because there is viscous damping, and then you have this damped oscillation type of characteristic where you have a wave nature which is a combined effect of space and time. So, it is a spatiotemporal propagation along with an exponential decay of the function. So, this is a very interesting solution that you can get as a part of this solution exercise through very little effort actually. I mean, there could be more complicated ways of arriving at this solution, but I feel this is one of the more convenient ones. So, this equation, this solution, let us try to make a plot of this solution, and then we will make some comments on the plot. So, if you make a plot, so the axis, this is, you have u by u0, and then this basically we are plotting y by this kind of plot we are making to represent the results. So, I have the plots with me. We will try to draw the plots quickly, and explain to you the different characteristics of this plot. So, the plot depends on omega t, right. So, So, there is this is omega t is equal to 0. So, you have a very symmetric plot of that for omega t is equal to pi. Then let me use a different color. We can plot. So, this value where these two intersect, this is very close to 2. Then we will plot for some other values. This is omega t equal to pi by 2. So, you will always have a symmetric value for the other part. So, you will have a symmetric, this one, this is omega t equal to 3 pi by 2, and from all these observations it is quite clear that it asymptotically gets down to almost 0 when you have this y so this is your delta. So, roughly at delta is equal to 4 into square root of nu by omega, the value of u becomes almost 0. So, this is the so called Stokes penetration depth. See, this number is not that important, it comes from the graph. So, but the important point is that the scale. So, this is essentially the length scale that governs the physics of the problem, and you can see that the plot of the graph etc., they will give only this prefactor, but the physics of the problem you can describe with this scale of delta just by looking into the governing equation and doing a scaling analysis. That is the strength of doing a scaling analysis before solving the actual differential equation. So, to summarize, so far we have discussed about a couple of interesting unsteady state problems illustrating the exact solution of the Navier-Stokes equation, namely the Stokes first problem and the Stokes second problem, and these problems are very classical problems in fluid mechanics, and these give you a lot of insight on how to use the relevant scales, relevant spatial scale and the relevant time scale to get interesting insight into the time and spatial dependence, combined time and spatial dependence of the fluid flow. Thank you very much. See you again in the next lecture.